Let's take a few minutes and look at how you can calculate the t-score, the p-value, and actually build a confidence interval for a two-sample situation involving means. So this is the context that we used in class. We're looking for evidence that the difference between the mean from the 2018 Chapter 8 test and the 2017 Chapter 8 test. We're looking for evidence that that difference is positive, suggesting that students are doing better in 2018. Well, the null hypothesis, if it's true, the real difference between the means would be 0. All right, so if random samples are independent, the standard deviation for the distribution, for the sampling distribution of the difference between the two sample means. So understand we have to take the standard deviation from 2018's Chapter 8 test scores. So that would be the standard deviation of the population divided by the square root of the sample size. We have to take that standard deviation, we have to square it, we have to take the same for 2017. We have to take the standard deviation from the sampling distribution and square it. But if these are independent random samples, we can combine those variances and then by adding and then take the square root to find the standard deviation for the difference between these two sample means. So of course, in most situations, you don't know the population standard deviation. So instead, what you end up doing is replacing that population standard deviation with the standard deviations from the samples. That's in fact what leads us to use t-scores rather than z-scores, that additional variability that we have by using the sample standard deviation rather than a known population standard deviation. That additional variability requires t rather than z-scores. So something to think about here. Let's simplify the formula before we even work with it. So here, if you square the population standard deviation, that explains the square that we get here. But of course, squaring the radical, we get just the sample size in the denominator. And the same thing happens for the expression in 2017. So we can take the square of that standard deviation, that's known as the variance then, just divided by the sample size. The square and the square root will cancel. So let's use those relationships down here, but instead of using the population standard deviation, we're going to use the sample standard deviation in 2018. That was 6.9. So we need to square it. The sample size, we took random samples of 10 in both years. So here is the variance for 2017. The standard deviation is about 10, so we need to take the 10 and square it. So this expression then will give us the standard deviation. So let's calculate its value. So we'll start with the square root. So, and I'm going to go ahead and put parentheses around this expression. So we've got to take the 6.9 and square it. And then we're going to divide that by the 10. Oops. Got to get back here and close my parentheses. Forgive me. There we go. So then to that, we have to add the square of the 10. Of course, I could simplify this. I could just cancel the 10s. I know that. So I'm not canceling the 10s just because I want to see how you'd be stuck entering it. This is a special situation where just by random selection, the sample standard deviation ended up being 10. I know that you could cancel those and make this a little simpler to enter into the calculator. I just want you to see what you'd have to do if, in fact, you had something different from 10. So our standard deviation is about 3.84. So I put that box here because I want you to see where we're going to use it below. So remember, there's a formula, a pretty fancy formula that you have to use in order to calculate the degrees of freedom that we could use to do this t-test or to build this t-interval. I'm rather going to use a conservative degrees of freedom. So this is much simpler. So it's found by looking at the two sample sizes, taking the smaller of the two and subtracting 1. Well, both of the samples are size 10, so 10 is the smallest one, obviously, and if we subtract 1, we get 9 degrees of freedom. So when I find my t-score and my p-value, rather, I'm going to use 9 degrees of freedom instead of the more complicated degrees of freedom, which we found earlier when we did this using our graphing calculator. It's about 15.99. So here we go. A t-score is a standardized score, so we are interested in a greater than alternative. So we want the likelihood of a t-score that's greater than our observed difference. So the sample mean from 2018 was 81.9. From 2017, it was 79.7. So that's our difference between our sample means. So if the null hypothesis is true, we already know that 0 would be the true difference between the population means. And we'll divide by the standard deviation that we just found, which is the 3.84. So I can just take that difference of, here we go, 81.9. I'll subtract the 79.7. Then I'm going to subtract 0, but I don't need to do that, and I'll divide by the 3.84. And this will give us our t-score. So we have a t-score of approximately 0.57. So what's important to me is that you realize that that's exactly what we got using the calculator when we did this question in class this past week. There we go. When we did our 2-sample t-test, we got a t-score of 0.57. So now we just need to justify the p-value. So to do that, these are not z-scores, these are t-scores. So the simplest way to do this is to use the tcdf command on your calculator. And this explains why we needed our degrees of freedom, because to use t-scores, we have to specify for the calculator the degrees of freedom that we're using. So if we go to second variables, I'll choose not the normal CDF command, that would be for z-scores. I'm going to use the tcdf command. So my lower boundary I will put in as the 0.57 that we found. So you need a relatively large upper boundary. I know with z-scores we tend to use 10. That would be fine here. I'll use 10. 10 standard deviations above the mean is relatively extreme. So there's 9 degrees of freedom. Again, your upper boundary, you could use 100, you could use 1,000, you use whatever you want. But again, you're going to see the p-value up here. So we had a p-value when we used the calculator command for the 2-sample t-test. We're getting a p-value of 0.29. What I want you to realize is when we did that using the calculator command, what did we get? Well, we got 0.29. So again, there's a slight difference in terms of the rounding error, but you don't notice that difference when you're only rounding to the hundredths place. So rather than using that incredibly complicated formula to find the more accurate degrees of freedom, the truth is in many cases, a conservative degrees of freedom is perfectly fine. We can just take the sample size and subtract 1, and we can use that as our degrees of freedom. And in fact, we certainly get a p-value we can use. So to build the confidence interval by hand, we need the degrees of freedom in order to find our critical value. So we're going to use that same conservative 9 degrees of freedom, and we need to find the critical value for 95% confidence. So remember, for 95% confidence, we have to think about the input that we need to use in the inverse t command. These are t-scores, so we have to use the inverse t command, not the inverse norm command. So if you don't have that command on your calculator, you'll have to use the INVT program. I'll show it to you both ways. So remember, with 95% confidence, we're cutting off the 5% of the sampling distribution that's most extreme, 2.5% at the top and 2.5% on the lower end of the sampling distribution. So to find our critical value, to find our conservative critical value, one way to do it would be to use the inverse t command. Here it is. There we go. So you have to put in, you could put in 0.025. You could put in the 95% plus the 0.025. That would be 0.975. That's what many of you are used to doing, so that's what I'll go ahead and do. We're going to use our conservative degrees of freedom of 9 and hit paste. So the critical value that we can use to build the confidence interval is around 2.26 for 95% confidence. Now, if you don't have that command on your calculator, you'll have to use the inverse t program. I'll show you how that works also. So if you run the program, there's the inverse t program. So this time, the first thing you enter is the degrees of freedom. And alpha is the amount that you're cutting off of each side of the sampling distribution. That's the 0.025. So it'll churn away for a second. And again, it'll give you the 2.26. There we go. So now understand the confidence interval. This is conservative. This is a conservative confidence interval. So for 95% confidence, it's actually going to end up being a little bit bigger than necessary. So we're going to put in our 81.9 and subtract the 79.7. So there's the sample difference. There's our statistic. We're going to add and subtract then our critical value. That's the 2.26. And then the standard deviation we've already calculated. The standard deviation is up here. It's the 3.84. So if I'd like to find my confidence interval, that's all I have to do. So I'll go ahead and clear the screen here. So the 81.9, again, if we want to find it by hand, minus the 79.7. So there's our statistic. The difference in our two samples is 2.2. So now what we need to do is find the margin of error. So I'm going to take that 2.2 and I'm going to add and subtract the margin of error from it. The margin of error is the critical value times the standard deviation of our statistic. That's 3.84. So the margin of error, we'll call it 8.68. So 2.2 plus 8.68. That gives us the upper boundary for the confidence interval. And 2.2 minus the 8.68, that will give us our lower boundary. So our confidence interval runs between negative 6.48 and positive 10.88. I'm 95% confident that the difference between the true population means for the 2018 Chapter 18 test, or rather Chapter 8 test, and the 2017 Chapter 8 test, I believe that that true difference is somewhere between, call it negative 6.5 and positive 10.9. Now notice, we call this confidence interval conservative because the lower boundary we found is just a little bit lower than the one we found using the calculator in class. The upper boundary is, again, just a little bit bigger than the upper boundary that we found using the calculator command in class. That's because the calculator command was using 15.99 degrees of freedom rather than the conservative 9 degrees of freedom that we were using. So we call this a conservative confidence interval because it's a little bit bigger than the 95% confidence interval really needs to be. So if you want to, we could actually use the confidence interval we found and we could work backwards to actually find the t-score that was being used, the critical value that was being used here. So our confidence interval was this, and our degrees of freedom was 15.99. So if you want to work backwards to find the t-score, the critical value, what you have to think about is the margin of error. So the margin of error that we found, we can find that margin of error. Remember, the margin of error is half of the distance of this interval. So if we take the upper boundary of the interval and subtract the sample statistic, which is in the middle, remember the 2.2 is smack dab in the middle of this interval. So the margin of error is just the distance from that 2.2 to the 10.345. So I can find that margin of error just by subtracting. I don't have to do anything super fancy here. So the 10.345, take away my sample statistic of 2.2. There's my margin of error. It's plus or minus 8.145. So understand the margin of error then is the product of the critical value, the t-score, and the standard deviation of the statistic. So listen, I know the margin of error and I know the standard deviation. So if I want to work backwards, I just need to take the margin of error that I found. That's the 8.145. If I take my margin of error and divide by the standard deviation of 3.84, what I'll end up getting is the critical value. And again, we're doing this to find the critical value that we would have needed to achieve 95% confidence using the real 15.99 degrees of freedom, which is the more accurate degrees of freedom. So here we go. We'll take the 145, and we'll divide by our margin of error, which is 3.84. And that results in a t-score of 2.12. So the idea is, I would want you to recognize for 95% confidence, if we were using proportions and using z-scores, that critical value is 1.96. So t-scores account for the additional variability that we get because we're using the sample standard deviation rather than the population standard deviation. So that additional variability leads us to a t-score that's just slightly higher. That's 2.12 to get us 95% confidence. And so, of course, when we built our confidence interval here by hand, we used an even slightly larger t-score because we were using a conservative degrees of freedom and easier degrees of freedom to find. That was the 9, the smaller of the sample sizes, take away 1. So again, I just wanted to take a second to take you through how we could, if we wanted to, calculate t-scores and p-values and even look at confidence intervals by hand if we wanted to do that for 2 sample situations involving means.